variety of magnetic ground states, anywhere from a long-range ordered antiferromagnetic state to what we know as spin ice. And this all depends on the details of what the crystal field ground states are and the type of exchange interactions that come about with these lattices. One thing to point out is that the anisotropy in the lattice is actually a local anisotropy. So the pointing into or out of the tetrahedron. So the well-known spin ices, they have moments that point only into or out of the tetrahedra, but there are other pyrochlores which have XY-like G-tensors like this, which is sort of the perpendicular to that direction. So how we have come to describe these materials most effectively is through this 4-parameter pseudo-spin 1/2 Hamiltonian. And the 4 parameters are 4 exchange parameters, and we often write them down like this: JZZ, J plus minus, J plus minus plus minus, and JZ plus minus. And what these parameters do is couple different components of these sort of pseudo-spin 1/2 operators. And so this is the full Hamiltonian here. And as experimentalists, one of our things that we can actually do quite effectively here is determine what these 4 parameters are, and then try to understand what the ground state of the model would be and compare it to the material. So for a terbium titanate, what we know now is that there is a very XY-like G-tensor. So the moments like to be in these planes that are perpendicular to the ice-like directions or the Z direction. But what we learned is that there's actually a strong exchange coupling between the Ising components of these moments, or of the pseudospin. And in addition to that, there's a strong coupling between the planar and Ising components, the JZ plus minus. So let's look at one of the problems here. So a terbium titanate has an anomaly in the low temperature specific heat around, let's say for now, 200 millikelvin. But the problem is that this is not a constant temperature for each sample. And furthermore, there's a different sort of sharpness associated with these peaks in different samples. But fortunately, most of the powder samples have the very high temperature, 265 millikelvin, and very tall, sharp anomalies, indicating that they have a higher quality and less variability from powder to powder. The single crystals, on the other hand, have sort of this sort of feature where you have a lower temperature anomaly from, say, 170 millikelvin up to 220 millikelvin. And in fact, all of the single crystals have a pretty low peak height associated with this anomaly. And so, correspondingly, there are some variations in the magnetic ground state that we know about. So, for instance, some of the samples show evidence for a ferromagnetic transition at this anomaly. And others, like some single crystal samples, do not show any evidence for a long-range ordered state. Okay, so for those samples that do order, the moment is coded from around 0.8 to 1.14 magnetrons, which is about 47 to 64% of the total saturation moment of the ground state doublet. Furthermore, some samples show evidence for hysteresis at the transitions, which confirms the first-order nature of these transitions. So let me show you some results that we've had since 2009 on a single crystal that has this type of specific heat. So it's actually got both signatures in it. It has the signature from the higher temperature transition and the lower temperature anomaly. But I'll point out here that the peak height is rather low. So one of the things that's quite interesting, and you'll see actually persists even in the best quality samples, is that as you cool down from, say, 4 Kelvin to 30 millikelvin, the energy versus momentum, SFU and omega, that you get from inelastic neutron scattering doesn't really change all that much. So you have this kind of broad continuum-like scattering, which is, this would be in the paramagnetic state, doesn't seem to really be modified by this transition very much at all, and certainly you don't see any sharp spin wave excitations that you would expect from an ordered ferromagnet. In addition, in this single crystal, what we see is a large amount of diffuse scattering. Here I'm But what happens as you go through the transition here is you don't lose this diffuse scattering, and instead you start to see it build up closer to the 111 Bragg peak, almost as if it was trying to become a long-range ordered state, but doesn't quite make it there. Yeah, so in this single crystal, we do not see any signs for a long-range ordered ferromagnetic state. But one thing that we could do, and this ended up being extremely useful, is that we can apply a magnetic field to single crystal samples and then measure the inelastic excitations as a function of field. And as you see here, if you apply a small field of 0.25 Tesla, you start to lift up this diffuse scattering, and it starts to organize itself into these sharp spin wave excitations. So this is a signature that we're entering a field polarized state. And if you go to high enough fields, you can imagine that this could be well described by a linear spin wave theory, which is what we did. So working with Leon Valent and Lucille Fabry, we were able to fit our data to this anisotropic exchange model. And you can see here we did this for 2 field strengths. And let me point out that the field was along one direction, 1 bar 0. And we chose this G-tensor in order to model the spin waves with. This was actually extracted from a crystal electric field calculation. And so doing this, we came up with a nice comparison with the 5 Tesla and 2 Tesla data, and we're able to robustly conclude that we had these 4 exchange parameters, the largest one being this JZZ, which, as you see here, is the largest and is ferromagnetic, which is, in fact, what you'd expect for a spin ice. So if these other terms were not present, you could say that you had a classical spin ice. So you might expect to have monopoles arising from spin flips in that type of scenario. Now, these other exchange parameters, which are smaller, but as you see here, not tiny, right? So this is the same order of magnitude. These could potentially be thought of as introducing quantum fluctuations into a spin ice model. And from that, you would have not just the monopoles, but you'd have emergent electrodynamics. So you'd also have emergent photons and emergent electrons, which would be extremely exciting. So if you take those parameters and try to understand what the ground state is, this was done by Leon and Lucille, and they did this using something called gauge beam field theory. What they found is that for large JZZ, there's 4 phases in the phase diagram, 2 of which are exotic. One of them is the quantum spin liquid, which supports this emergent electrodynamics with the photons, monopoles, and electrons. And then there's another interesting phase here, the Coulomb ferromagnet, which is a partially polarized phase that's related to this quantum spin liquid. So it has the same quasi-particle excitation, but it has a partially ordered moment. And then these other 2 phases are more conventionally ordered phases, a ferromagnet and an anti-ferromagnet. And so, depending on where exactly these phase boundaries are, keep in mind this is a type of mean field theory, so that these could be shifted around a little bit. You could think that ytterbium titanate might be close to some of these phase boundaries, which may explain why it's so sensitive to disorder. Furthermore, recently there's been some very nice work by 2 other groups who have come up with another alternative set of parameters, actually 2 different sets of parameters, but they're close to one another, which indicates that ytterbium titanate may lie close to a classical phase boundary. between the displayed ferromagnetic state and these two anti-ferromagnetic phases, psi 2 and psi 3. And so in this scenario, this would also be a case in which we're lying close to a phase boundary and have